So what are these types of variables? They're, for instance, about being energetic, having concentration or lack of concentration, agitation, loss of interest, etc. So they're very reasonably clearly interpretable, but they're difficult in the sense that, yeah, we have a particular construct, but how do we measure them? We ask people questions, but do they exactly interpret them in the same way as we do? There are many, many difficult things about this. But we try to make these kinds of graphs. And I'll first try and explain what this then means. What does such a graph mean? If we look at it from a higher level, basically what we see here is what's called persisters and remitters. So most of these people are patients. They suffer from major depressive disorder. And these people are sometimes in and out of particular institutions or in and out of treatment. And we refer to them as persisters when they don't really get out of this depression. They remain in most of the time exactly the same state. We call them remitters when they actually get out of this state. And for longer periods of time, they stay relatively healthy.
Is such a graph related to a single individual and then links are made over time, or is it aggregated over different individuals?
There are different ways you can do this. In many cases, we hope to have data from a single subject for a longer period of time, and then you can make a graph like this for an individual. But in many cases, we don't have these data. These data for these graphs are made from more than one individual, a few hundred individuals. Yeah.
Is there correlation between the symptoms?
Yeah, I'll explain a little bit more, something like correlation. Yeah.
One question I was one symptom I'm not seeing for is retardation.
Yeah.
So,
Yeah, sorry. So it's psychomotor retardation. Okay. So you have the feeling that you're a little bit slower than usual. So yeah, it's a little bit related to agitation, but it's something like this. Yeah. No, and there's also this one. So this is hypersomnia and insomnia. So you either sleep a lot or you don't sleep a lot, which makes sense to be correlated negatively. And hypersomnia, if you sleep a lot, it's become energetic, which also makes sense. So in many cases, these things do make sense. But what we see from these types of graphs is that there are many more connections, but there are also the coefficients between these, the associations are stronger. And that leads us to believe that maybe persisters have these stronger relations that maintains the particular state that they're in. And remitters have not that many and less strong associations between these variables, and that may be a reason that they get out of these states a little bit more easily. But basically, the question that we have is how could these networks, if you make them, I'll explain a little bit more on how you make them, how can this tell us something about what eventually will happen to people? So what are the dynamics?
So a little question. So that you talk about associations, but
yes,
you don't know anything about causality.
Yeah. No, we usually don't. For these graphs, we certainly don't. But there are some cases that you can apply. So you could apply some of the theory by Pearl or securities and suggest, well, there's no evidence for confounds. And so we might reasonably suggest that there's evidence for a causal relation. But it's generally very difficult to do. Yeah. But if you have temporal information, then you at least have another argument to suggest, well, this came before the other event. And so it's not to say that there's no spurious connection, but it's more likely to be causal.
No, but then you need like time series.
Then you need time series. We often do that. It's very common now in psychology.
But you're interesting to see how each symptom is influencing the other.
Well, we're interested in that as well, but that's specific to treatment. But one of the questions we also have is this kind of graph where you have more edges, more connections, things are very strongly associated with each other. Does that lead to different dynamics than in the case that it does not, that the influences are not that big?
So the remitters are people who experience a depressive episode, like a shock.
Yeah, they get out of it. Yeah. and they remain out of this or remaining in a healthy state for a longer period of time. Yep. Yep.
And just to be clear, so the persistence, the difference is one is clinically diagnosed, so they have at least 7 symptoms activated. And the this is then correct. So
You only need 5.
but only need 5.
Yeah, bingo, yeah.
These are the ones on the left are the people who retain 5, but the whole period is.
Yeah. Although they switch, of course, in which ones.
Yeah, that was my next question. So
Yes.
they can move between different 5.
You're allowed to move within these. Yeah, so many people are different in that respect, right? So you don't need the same 5 symptoms in order to be depressed. Any of the 5 symptoms, these are not all DSM symptoms. There are 9 symptoms, and here there are 11 variables, but we included sleep variables and one other. Yeah, I think feeling guilty is not part of it. Anyway.
Appetite changes.
Sorry?
Appetite changes.
Appetite change. Oh yeah, that's what. Where is it? Oh yeah, no, that's weight. Yeah, weight and appetite. Yeah, sorry. So anyway, we're interested in these kinds of dynamics. The way we define these edges is basically in terms of conditional dependence or conditional independence. So in terms of conditional dependence, we say that 2 variables are conditionally dependent if the joint distribution cannot be written as a product of the marginals given any other set of variables. But basically, we look for these patterns in terms of the co-occurrence across people or within people when we have time series. And we make a graphical model out of this so that the nodes, each of the nodes we associate with a random variable, and the edges are the conditional dependencies, and we look for them in terms of cliques. So we can decompose it. So if there's a larger number of variables, it's relatively easy to decompose it in terms of nodes that are completely connected to each other. And then you can basically compute this locally for each clique separately and then combine them in the product. So that's one way to do it, but then we have to assume something about the data. What kind of distribution are they from? So you can do it non-parametrically, but it requires usually a lot of data, which we often don't have. So we often assume that the data are binary and that the Ising model is a reasonable assumption. Right? So we cut off, we don't have any higher order interactions. And then we can basically do a logistic regression and say what's the probability of each of the nodes given all of the other nodes. Right? We have no idea of the structure in general, so we need to fill in something. And then we determine the connectivities and determine these will be the coefficients here between these variables. That's how we define these coefficients and determine the network.
Yeah. When you binarize, because these are Likert scale questionnaires.
Yeah, some are binary and some are Likert. Yeah.
So when you binarize, you just pick a threshold which is clinically proven or just statistically, or
if we have clinical information about that, we use that. But sometimes we only have the data, and then we need to decide what threshold is. We do differently. Sometimes we use IRT, item response modeling, to determine what the optimal choice is there. Sometimes it's the median, and sometimes it turns out that it doesn't really matter.
Okay, so maybe we'll dive later. How is distributed the correlations of all these symptoms?
You mean what the distribution of the coefficients?
Yeah, the whole distribution.
Well, that depends on the sample you're looking at. So for this, the distribution is much higher, so that most of the values are large, and here most of them are relatively small. So it depends particularly on the sample. Mostly what we are also interested in is determining, well, is there any of these variables that seems dominantly important? And so here, for instance, this one might seem to have a lot of connections, strong connections. So is this a point where you could intervene? Is this a point where in treatment you would say, well, that's something to focus on? Sorry, the central node, yeah. But centrality is not always, I mean, if you think of these as causal systems underlying it, then it's not necessary that this is an interesting target for treatment, because it could all be in degrees, high in degree, but very low out degree, and then it doesn't have an influence on the other things. So, yeah.
Why do you choose to represent the binary states as -1 and +1 and not 0 and 1?
Yeah, so that's a good question. I mean, here it's a -1 +1, but I think actually for this data analysis, we used 0 and 1, but it depends on the context also. So if you think of symptoms, you can say, well, it's more likely that they're absent or present, and that's 0, 1. But in some cases, we also talk a little bit about a change. So usually weight is determined in terms of their change, and then it would be negative or positive. So it depends a little, but they're all modeling choices, yeah, and not easy to make. Also because, sorry, I'm just finishing up. Also because many of these questions and the type of reasoning behind it has a long tradition without any formal modeling. And they just keep on going because that's the way they do it. And then we have to sort of fix everything at a later point. Yeah.
Just a couple of questions about the Ising model.
Yeah.
So this external field weight, is that a medical intervention or something that's going to try to shift the system towards one or another state? Is that what's going on with that child?
It's everything together, basically, because so the interpretation usually is in terms of, well, it's a particular thing of this variable. It's associated to this variable particularly. So we have these external fields separate for each of the nodes. So we tend to think of them as a characteristic of a node. So it makes it more sensitive or less sensitive to change, to flip from -1 to 1.
So you've got a node-based external field.
Yeah, but we actually don't know what it is. It's an aggregation of many things towards this variable. Yeah.
There's some of these personality.
Yeah.
Right.
Some genetics, personality. Yeah.
And then what is the function? What's the purpose of having an Ising model? I mean, are you looking for some kind of phase transition between more or less healthy and more or less pathological?
Yes. I'm coming to that.
Oh, okay, sorry.
No, that's okay.
Don't forget.
Yeah. No, we're interested in the dynamics. How do things change eventually if we have a little bit of information about a particular group of people, or preferably about an individual, and then what are things that can change and what will happen over time.
And this external field is constant for every symptom, and also the couplings.
No, they're not constant, so they can differ between each of the symptoms. You can have different external fields for each of the symptoms. So the effect of something external or genetics may be different towards each of the variables.
It's different. This is a small difference from the magnetism version, because the normalizing model would have the same field.
Yes. Yeah. In that sense, it's different. Yeah. But basically, our assumption is we have no clue what's going on. We try to work out if that's similar. So you can also test, of course, if these are relatively similar within a particular model or a group of people. And if they're similar, you'd say, okay, so there's just one thing affecting each of the nodes in the same way. Yeah.
If you've got longitudinal data for 100 patients, for each symptom, presumably if you're healthy or unhealthy, you'll see some frequency. Changes in these things. Also, you need that for the correlation. So can you estimate some sort of time scale for these symptoms? Whether they're really disconnected, connected, right? So the changes in your sleep versus the changes in your energy.
Yes. You can do those sort of things. But within this network modeling, we haven't done that much yet. Yeah, but there are many different ways of looking at these types of data.
And that would give you maybe some estimate for this external field, how it differs.
Yeah, that's a good idea. Yep. And basically, this is the modeling part. I mean, this is only quite old, from the 70s. Besaf who introduced this. But nowadays, we often work with sparse solutions. So we assume that because there are lots of parameters to estimate, we assume that basically few of these edges are really there, or if they're there, they're quite small, and we don't usually have enough information to see them. And so we assume a sparse solution, and we assume what's called a restricted eigenvalue, or there are different versions of it. But you assume about the modeling that it's reasonable to do. So the covariance structure that we're interested in actually is to some extent non-singular. And then you get reasonable recovery rates in the sense that you get very few of these edges that are actually not there. Right, so that's our main point. If we infer that there's an edge, then we want to have quite some confidence that it's actually there. So we miss a lot.
Just one more question.
Yeah.
So I'm still got my head in that Ising model. What functions is the volatility is the temperature in the synthesis?
Not, because the temperature is not identifiable. So in the statistical sense, it's multiplied.
And you're just looking for the
Yeah, we don't know it. So basically, it's conflated with both the external field and the interaction terms. Because
Okay,
so we cannot
assume it's constant.
We assume it's constant. Yes. So we assume an equilibrium distribution at a certain point when these people were measured. Yeah.
Okay,
Yeah.
that makes, yeah, thanks.
Now, one of the problems we have is that often the data are not binary. They're on a Likert scale from 1 to 7, 1 to 4, or also very often -3 to +3. And so you have different kinds of models, and we're often not interested in the strict, in the Potts model, for instance, where you could also have these multiple states, because we're also interested in interactions where you have -3 and 1. And what kind of contribution would that have towards the Hamiltonian? So we want all these values to matter, also the sign, and also the zero has a specific interpretation. For instance, in these cases, something would be absent, not negative, not positive, but it's actually absent. That's also an important part of this type of modeling. So there's a little bit of a misfit in terms of data and how we tend to think in theories about how this works. And
I'm sorry, I think the interactions, what is the -3, 1?
so these are the values that that the variables can take, right? Instead of just -1 and +1. And there's an interaction, so the multiplication of two nodes, suicidal thoughts and insomnia, for instance. And this interaction then gets to be -3. Right? So there's a value of insomnia 1, suicidal thoughts -3, and that's the interaction between them. So it's
I think we might be able to incorporate it. Okay, later.
there might be what, sorry?
Maybe we can talk later. I think that there are some sophisticated versions of
Certainly.
the Potts model that would incorporate something like that.
Yeah, also talked to Julia just a moment ago.
Yeah.
There are different versions. You can also look at distances or do other things. Yes, certainly. I'll talk a little bit about the Ising model because everybody knows it so very, very quickly, but I wanted to show it a little bit because it's a thing we compare it to. And so we only have variables in -1 and 1, and often a lattice is used, or a random graph, or a small world, or scale theory, or many different kinds. But we are interested in not only what this model says and how it interprets theoretically, but also in quantitative fashion, what will happen over time, what kind of things like phase transitions are important. And so if the Ising model with the temperature that's now here, that wasn't there before in the estimation because we cannot identify it, the external field, the interactions, and just a -1 and +1 values of these variables. And of course, the partition function, which is very important. And we work towards the mean field to get a qualitative idea of what may be going on. And so we assume weak correlation between the nodes. Usually assume a regular graph, so each node has a fixed number of connections. And the mean field then gives a reasonable approximation of the qualitative behavior. And we look at typically an order parameter, that's the magnetization. So that's the expectation of a generic variable within this model. And that's the physics notation for the expectation. And we often approximate this in the mean field by just summing up and dividing by the number of nodes. And hopefully, if you have enough, that's a reasonable approximation. So that's what we look for in the mean field. And then you get these pictures like this, where you get the spontaneous magnetization as a function of the inverse temperature, right? So it's warm here and it's cold here. And you see it increase, and the continuous line is the prediction from the mean field, or actually it's the prediction that you get from the lambda theory of the mean field. And that's here. This is the usual way of writing it in terms of the inverse temperature and the critical temperature, the interaction strength times the degree of each node. And so this tells you a lot about what can change, what can happen in terms of the temperature. And you can also look at this in terms of the external field. If you change the external field, in what way will it change the magnetization? And that's relevant for the Ising model. Although it works on, in strict assumptions, it works very well, but then you look at different types of graphs, and then it seems not to work always that well. And I'll have a little bit later on to describing some issues related to what kind of graph this actually works for. And so the only thing that we change now is in terms of the labels, right? Or the labels, in our case, we say they're not really labels, but we say we bound it between -1 and 1, and we look at the different values in between. So it's not just binary, but it's any number symmetric around 0. And you could also think of this, of course, as being from -k to k, and then not dividing by k again, but we do this because it makes math a little bit simpler. And so we bounded it between -1 and 1. And this model already existed. It's not a new model. It's been introduced, I think it was somewhere in the late 60s by Suzuki, who looked into this in terms of correlation functions. And later in the 90s, it was introduced in terms of statistical applications by Rabe, but they were only interested in defining it like this, also with the bounds between -1 and 1, and then determining parameters, statistical estimation. And so these are just typical examples. So we define a k, and determine the number of values that the variables can take. And then we're interested in the mean field. So we apply the mean field idea. So we take the assumption for the mean field, which is the weak correlations, so that you can basically take away the product of these variables and only look at the sum, which is related to the order parameter, of course. And with this mean field, you can take the Gibbs free energy, or which I call in statistics the cumulant function, and determine moments from there. So usually I'm used to looking at this cumulant function and determining first order, second order moment, or higher order moments, etc., etc. And I was quite surprised that in physics they do exactly the same, then for slightly different reasons, and all the terminology is different, of course. But it looks quite similar, except that you now have a sum over the states of X, which is a larger set than just the binary one. So this becomes a little bit more complicated because you have the set Q, which is from 0 to 1 with all of the in-between possible states that you could have. And then this is a picture of the free energy. And you see, so here's the Ising to compare. And it looks similar qualitatively, of course, but it seems to be easier to get from from the negative to the positive state here. But it also turns out it's not too visible here, but actually these minima are a little bit closer towards 1 than in the actual Ising model. And it's a little bit easier to see here from this iteration map. So if you apply the mean field once to a particular value that you start with, then you see that here the Ising model gets to exactly -1 and 1. And the Ising 3, I've called it here because k equals 3, so they're from -1 to 1 with variables in between. You see that it doesn't get exactly the fixed points to not to get to -1 and 1, but a little closer to 0. And this is the mean field, so you get a sum of these. Sorry.
This is for fixed temperature, then this self-consistent.
Yes,
variable.
fixed temperature. Yeah.
And you arbitrarily choose like 1 or something.
Yeah, of course, if you change the temperature, then the function changes. Yeah. But here I chose arbitrarily, I think, I forget. Yeah. But then, of course, we're not only interested in looking at these things, where the minima are and where the fixed points are, but also looking at the phase transitions, for which we use the lambda theory, which is basically looking at a Taylor series of this low partition function and then computing the coefficients of the Taylor series, approximating it. And basically, this is what we get from this theory. So the even moments are 0 and the unequal moments are not 0. And we keep this, so the first order transition remains. And we see that these coefficients, so this is the first coefficient A1, and the third coefficient here is a little bit more complicated, and it comes about because of the counting of the categories. And it's not very difficult, but the factor that we were interested in or became interested in was this R, which is 2 times K. So that's the number of plus 1. That's the number of categories divided by 6K, which also comes about just by counting all of these categories. So we have this part, and from this we can determine exactly like you do in the Ising model. You can determine what then are the exact points where the magnetization changes from 0 to 1. And we have this factor K, and you see here the original Ising, and you see that it's shifted here, and that's predicted very well by this value R. And R was the number of categories that you had, or the number of values that the variables can take, divided by 6K. Right, and these points are the prediction or the actual mean field, and this continuous line is this positioning of the line derived from the lambda theory. And you can also do this for the external field. So where from the external field, how does it change this value R? How does it change the curvature here or the change in magnetization depending on the external field? That's like this, and it also seems to be reasonably well when all of the assumptions are satisfied.
So you're comparing their lambda theory to the mean field, not mean field to the exact.
And not, no. Lambda theory in terms of this approximation, so the approximation that you do of the free energy to the, so the dots are here the exact mean field.
Right.
Yeah, that's what you mean.
Yeah.
In some sense, in some sense here, the behavior of this doesn't change so much.
Doesn't
You
change so
actually-
much.
Yeah, it
No,
doesn't change.
no. No. So you could say, well, it's extremely similar, yes, and we were very pleased with that because we would hope that the interpretation would remain similar if you have a different type of data, and it seems to do that.
Around the phase transition.
Yeah, around the phase transition, yeah. But also, I mean, if you look at the free energy, there are two minima. So qualitatively, it seems very similar. Yeah.
So if you send k to infinity,
Yes.
you end up with like a Gaussian
Well,
or something.
if you send k to infinity, then you just get 1/3, right?
Yeah, I mean, so what happens to the phase transition? Because you end the Boltzmann distribution becomes like a Gaussian over real variables.
It becomes like a Gaussian, yeah. Yeah, I would say so. Or well, if I fix it between -1 and 1, and then it's sort of continuous, in it is continuous, and then we looked at the continuous version. But then so if you use the measure, the probability measure that's continuous, then the behavior is much less interesting.
Right.
So in that sense, they're not the same.
So what would happen? You would see this view line shift to the right and flatten out.
Well, if you increase k, you see it going to the left a little, and then it would, at some point, if you change the probability measure, then it would flatten. Yeah. But you would remain seeing it, and it would be so. It would go this way a little bit more, and then if you actually change the probability measure, then it flattens. Yeah.
And that
Sorry.
Actually, I want to one quick. I lost the connection with mean magnetization to your original graph about different states. It's just that you want to say that if the sum of all these different variables relevant for depression would be larger than something, you have a transition, you get the depressive states.
Yeah, so that's one way of looking at depressed and healthy states. Yeah, so if all of the symptoms are on, so to speak, then that's we consider that as being in a mentally problematic state, and that you can qualitatively measure with these phase transitions. Yeah.
Related to that question of maybe these were already investigated, but I don't know whether the infinite k limit maps into the continuous spin systems like the XY model.
Well, I don't think it maps exactly onto the XY model, for instance. But I didn't look into this a lot. This is we started this just before Christmas. But I did look into the continuous Ising model where you bound it between -1 and 1 or between 0 and 1. And there you don't see the magnetization if you use the continuous probability measure. But if you just use discrete probability measure, but with a high number of k, you still see magnetization like this. Yeah. But yeah, I didn't use it up to a few million, but yeah.
But also the infinite solution of the XY model is a Gaussian.
Yeah.
Yeah. Nature is the vectorial spin. Here is more a scalar spin. So different from the state.
It could be a curious that.
You had no.
Well, maybe actually, like, what value of k is the Ising model? Because it seems like k half or k 0.
No, so we plug in the 0 always. So if you choose k equals 1, then you already have 3 values. Right? You have -1, 0, 1. So it's never exactly the same as the Ising model.
There's no limit to Ising for k goes
No.
to 0.
No, because we always want 0 in there for us, for the type of data we are modeling. Yeah.
I guess maybe by choosing the external field, you could maybe.
You could relate it more to the Ising model, I mean.
No, I don't think so.
So if you look at the phase maps in terms of external field and inverse temperature, then you see the difference in the Ising model, and regular Ising model and the general spin Ising model, that you need here you need lower temperatures in order for the magnetization to get working, which is also what we see from the previous pictures. And we checked it with Metropolis algorithm to see if you could find it just using the distribution and seeing if we could find the magnetization also corresponding to the ones that we get from the Landau theory, moon field theory, and that seems to be the case also for the external field. But now there's an interesting phenomena that by increasing the K, you decrease the width of the hysteresis. So that also seems interesting, and you looked at this a little bit further with the Tuam, and you see that it's indeed goes here. So it closes a little bit, but it seems to converge at to some point. But of course, this depends also on the temperature that you have. So the width also depends on the temperature. So for a fixed temperature, you get these kinds of figures. Okay, and then of course the question is, we don't know in psychology, we usually don't know a lot about the exact structure. So what happens to the mean field if you put it on a small world or on a scale-free network? What will happen? And in terms of this mean field here for a small world, of course there are particular settings, but it certainly was modular in the sense that there were relatively many connections within each cluster and relatively few between each cluster. And then it seems to be still quite accurate, right? So it moves, so the degree, the average degree is also included in this factor determining the exact point of the phase transition, and it moves it towards here. So the degree of the whole network is of course dependent on what kind of network you have, and so it will move this location also. And that seems to be reasonably well. But if you put it on scale free, well, you can see the location may be okay, but it's certainly not doing very well. But up to a point, it's okay. But the question is, of course, and we also looked at this is a slightly different approach where we say, well, what happens if we don't just have a normal network, but we say we have a stochastic cellular automaton. You apply a particular mean field. We use the binomial process here, and you look at the bifurcation and look at the data that we generated based on real networks, and then you see that it predicts reasonably well. And of course, we didn't know if the real world networks were actually random graph, but they seem to be, some seem to be associated with, so we did model fit, and it seems to be a good representation in some small world. And that seems okay, and depending on the size of the time series, so this is 50, 500 time points, 5,000 time points, you see that it holds up reasonably well. Most of the points, these are all individual points of the network that were reached in equilibrium, and you see that it predicts reasonably well.
Sorry, maybe this was too fast for me to understand. How do you connect this with the other Ising model? What are the cases?
No, so this is just this is not to connect it up to the other Ising model, because it's a different type of model. But it was just to show, okay, so if you look at mean field approximations, they seem to work generally well, even though you don't have a fixed graph, so not a regular graph with every node having the same degree. But on the random graph in small worlds, you see that the
so these are mean field approximations of Ising models and graphs.
Well, of stochastic cellular automaton.
Okay, right.
Yeah, so slightly different. And so we also use a slightly different model. It turns out that we use the binomial process for the mean field. So it's slightly different, but the approach is similar. And you see that the mean field often works quite well. But the question was, why, so how do you know when it works well? When does it stop working? What's the point that it turns out to be a bad approximation? I think there are some examples where it's a bad approximation, but there's a specific paper by Lourens and others who looked at this, and they looked at several different models and then at what kind of graphs, real world graphs, it would work. And one of the models is the very simple infected susceptible model, where I is the density of the infected and beta is the spreading rate. And they either have or have not an additional term to take into account the correlations between the degrees, the different degree nodes. And that's the difference between the UMF, the uncorrelated mean field, and the correlated mean field. So either in the correlated version, we take into account the differences in degrees between the nodes, and in this version, it's uncorrelated because you do not take that correlation into account.
There an I missing in the second term of the line?
It
should be non-linear, right? Because now it's linear.
Yeah. It's a good question. The normal I is, yeah.
There should be I.
Another I
times I, right?
There should be an I here. Yeah. Yeah, because this is the S. Yeah. So usually you assume that there's no modularity, but it was quite clear that in modular networks it often does work. At some point it will stop, of course, if there are no connections between the modules, but and the absence of dynamical or correlations between the nodes, so the effect one node has on the other. But that's not the only thing that probably matters. So here's a graph of the internet. So websites connected to each other, and it has number of nodes. The average degree is usually important. That also functions a lot in the mean field. And then they also looked at the average degree of the first or the nearest neighbor, first neighbor or the nearest neighbor. So look at a node and all of its nearest neighbors. What's the average degree there? And this is quite high, I think, especially if you look at the average degrees. So there are some nodes that are a very low degree, but also many high degree. And if you look at a different type of network from the electronic circuit, you see that it's very similar. For the previous, the average degree was 4, and here the average first neighbor degree is very low. And then the mean field solution doesn't seem to be very accurate, even though the average degree of the network is quite similar. So it's not the average degree, but the degree of the neighbors, the average degree of the neighbors. That seems to be most important. And here you see them both. And you see that there's a huge difference in the degree of the neighbors. That seems to be key for determining whether the mean field can be accurate or not. And the idea is that if the degree of the neighbors is quite small, then the effect the nodes will have on each other is relatively large, right? If one of them is on, it will have a large effect on the other. Whereas if all of the neighbors have a large degree that are connected to many things, and their input will be relatively minor. That's the idea.
Is it not just also just path length?
Is it not just path length?
Is I guess in the internet one you've got
Say it's
a like structure.
Yeah.
So I suppose the floor is like 250, so you get something that resembles P1, but here it's so the variance in the degree distribution is much narrower.
Yeah.
Right.
I'd say that's quite correlated. Yeah.
This also makes sense because it's like this one node that's super connected does the averaging for you.
Yeah. Exactly.
Could you relate just with the statistics, like if central limit theorem holds, then exchange the whole distribution by the mean is a good approximation, and is the definition of mean field, or is that statistically behind?
Yeah, that sounds quite reasonable. Yeah. So yeah, if you can, if it's a good representation of all the others, and so there's a lot of averaging going on, and then the central limit theorem would come into play. Yeah.
The electronic circuit seems to be almost lattice.
Yes. Yes.
The mean field makes sense.
Yeah. Yeah. Okay, but I find this general question in general interesting because we use it a lot to sort of get a qualitative idea of what a model can actually do, and then if it turns out that for many of the networks that we actually look at, it doesn't really have it doesn't yield a good approximation, then it's useless for us. But I didn't find a definitive answer. But maybe you've seen one.
And maybe,
And that's it.
Somehow some measures on how fast information propagates in comparison to fully connected, because fully connected will be mean fields.
Do we have information on it?
But if you have a fully connected pairwise model, you can rewrite it down as a mean field.
Yes. Yeah.
Maybe there is it will be somehow you will need to compare how far your network is from a fully connected model.
Yeah, but in what way, right?
I would say like how fast information.
Because if I look at the modular network, and then path length may be more obvious to use, because path length in a modular network can still be small, but for the scale 3 it can also be usually a bit higher. So,
yeah, but that also means that's the way information decay in your
it's different.
It's different, right?
Yes.
In one case, you
Yes.
keep information for a very long time, whereas in the one where you are mixing very quickly, you lose information very quickly.
Yeah, but I would say if you start with a completely connected network, a graph, and then you just take away some of the edges, then in few cases it will become modular. So in most of the cases, if you randomly delete the edges, it will remain quite good to mean field approximation up to a point where there are very few edges.
Yeah.
But if you start, if it turns out to be a very modular or bipart, or not even bipart, but two component network, then of course it doesn't work.
Yeah.
So for the whole network. So I would say that, yeah, it's not the closeness how.
Fast information is decaying in the network in comparison with.
Oh, with information, yeah.
Not just removing, but how compared.
Yeah, I think other people also suggested that you look at betweenness. So if it turns out that there's only few nodes that lie between two components or one component, then it's also measuring. Many things I think are correlated. So the path length also sensitive. Yeah.
But I think back of the networks you started with in the beginning.
Yeah.
Are they more like the internet, or are they more like the electronic circuits? Do you expect the
much smaller
to work or not?
Is it the size?
Yeah, I think the size
Way
is
smaller.
But the size must matter a lot, because those two examples, the internet one is like.
Yeah, exactly.
20,000 nodes,
Yeah.
and then the other one.
Oh yeah.
Only
So I would
500.
imagine that the mean field approximation
Well, depends on the size.
and becomes smaller, and then the example you showed at the beginning at around like 10 or something like that.
Yeah, 11 nodes.
Yeah, no, also when I looked at the Bloom-Capel model, the slight variation again on the Ising model, we looked at the conditional distribution, and it's almost identical to the mean field solution that you have. So in terms of, and then for the conditional distribution, it doesn't really matter what the exact graph is. It has to be connected somehow to most nodes, otherwise there's no contribution of the other nodes, of course. But in that sense, the mean field for smaller networks could certainly work just as well. But if you make it large, and then there's a particular structure that would make it indeed more sensitive to path length or the degree of the nearest neighbors. And so size in that sense, I would say yes. Yeah. Yes.
So the graphs that you had from actual data, like what you were showing in the beginning.
In the beginning, yeah.
How many of those do you have enough to collect reasonable statistics on the properties of the kinds of graphs that arise in this setting? I mean, the random graph models are often really crappy fits for things that happen in real life. And if the data is good enough and the size sets are smaller, is it possible simply to generate families of graphs with similar statistics instead of fitting a random graph model that doesn't have the right, might not have the right properties you want, but I don't know how much data you need.
Yeah, so it depends on what kind of group you're looking at. So if we think of patient data, there's often not much data. We have, I mean, maybe a few hundred patients, but often you have one measurement for each patient. And you would like to have, ideally you would have like time series or a lot of measurements per person. But we often don't have that. And if you switch groups, so if you say, okay, so I'm looking at depressive people with major depressive disorder, then that's fine. But if I switch disorder, it becomes completely different. And so and it's also the case that, if I go back to the beginning, it's also the case that if I, so these are graphs taken from many people, but since we also allow for people to have different symptoms that lead to the diagnosis of having a depressive disorder, then it's also very likely that each of the networks for each of the people is different. So then this is actually a mixture of many different graphs. And we try to solve that a little with a Fortuyn-Castellijn model, which is a model that defines a joint probability over the nodes and over the edges, but it restricts the connectivity of the edges in a particular way to make the connection, the coupling between the nodes and the edges.
Yeah, I once tried to do something that's similar. I was creating Ising models on the UK Biobank.
Yeah.
And I ran into a funny problem, namely that all these models automatically converge to critical Ising models because they had to reproduce both men and women.
Yeah.
Which are sort of two phases.
Yeah.
Because what men were high magnetization, because there's a lot of like muscle mass. And that kind of was a big problem because that means that the metropolis sampling no longer works and stuff.
So there's a mixture of graphs, a mixture of different properties, all tried to put into one Ising model, which is basically not.
Yeah, but if I understand correctly, that you're also kind of interested in having one Ising model that could do both.
Yeah, well,
the remitters and the persistence.
No, my interest is actually in individual ones, but as a proxy, we use, and in psychology that's quite standard because it's a young science. In the beginning, they looked at individuals, but then somebody thought, well, what you could also do is just give somebody a questionnaire, then brainwash them and give it again. And that's exactly the same as looking at different people. And then the whole of psychology got really excited because we could just exchange one person for many people and pretend that we could measure them lots of times. And so that's why we end up with this, because now many people still measure a lot of people once and then put them all together and say, well, they're just basically the same. And to some extent, of course, it's reasonable because many of the characteristics we have are the same, but in terms of depression, it's clearly not. So that's an issue. So ideally, we would have a lot of information from one person and model that person specifically. But of course, there are lots of other annoying things when you work with time series. Like for many models, you need to assume stationarity, which is very unlikely, especially if you assume or if you induce a particular type of treatment. Then you know that it's not stationary because you induce a particular change on many of the variables.
All these people are in treatment.
These people were all in treatment, yes. Yeah.
The other question I had about this, because the idea that these people are clinically depressed, so 5 symptoms are activated, but they move around. So these correlations pick up like robust clusters, I guess, that fluctuate somewhat, but also movement between clusters. So
well, if you say they speak up, that's what they detect. Yes.
That's what they detect. Yeah. So, but you will have both. So you will have both the people who are kind of robust in these 5 that are fluctuating, but also people who are moving around this way. So is there a notion about because it's only 5 symptoms, different types of depressive disorders? So is there qualitative difference between somebody who has suicidality?
Yes, certainly. Yeah. Certainly, if people have suicidal thoughts, then you would treat them differently than somebody who just has feelings of guilt and agitated, etc., etc. But this is not a standard in terms of research. So the traditional research paradigm basically says, oh, this is depression. Basically, there's one underlying thing in your body that determines all of these symptoms. So that puts them on or off or whatever. But of course, nobody was able to find depression somewhere in the body. And so a biomarker or something, doesn't matter, even if, but the construct was there. And this is also done with intelligence research. There's intelligence, and this makes you smart at math, or makes you able to answer a lot of the questions on history correctly, etc., etc. And people have also been searching a lot for the intelligence thing inside people. Oh yeah, but of course, this isn't the case, and so yes, we look at people who are different, but from the perspective of this disease type model, it's very logical that people can have different symptoms, because that's what this theory says. But we are interested in how they influence each other, because they certainly do.
Yeah, I'm just wondering if you could isolate the people who have these robust clusters of 5.
Yeah.
And then separate their graph with the people who are more than the others. Maybe that's something to do with suicidality.
Yeah, that's because now we're collecting a lot of data through phones. That's now starting to be possible in the sense that we have enough people to categorize them. But still, it's very difficult to get actual patient data, because patients typically are not willing to do this questionnaire. It's very boring.
But if you feel bad already, it's not going to help.
No, it's not going to help. Do you feel depressed? Yes. Yeah. No, it's not going to help. No, it's terrible.
One question more like relates to the beginning and the end, because the beginning was more data driven.
Yeah.
And the end, you kind of
we moved away completely
to the midfield version of the externalized Ising model, and then you compare midfield with the exact. How do you want to bridge, or how much can you get from the midfield that is helpful for the pathology structure?
Oh well, because we estimate these kinds of networks, and from these networks we can, assuming some temporal structure that for an individual, we can try to figure out if it's reasonable that there are some types of phase transitions. And one way we did that was in the stochastic automaton version, where you try to work out what position in terms of the parameter somebody has with respect to the bifurcation. So is it possible that somebody switches states, or if this person is very stable? So that's one way of doing it. One way of connecting up this network that you have, and how does that connect up to possible phase transition in terms of the bifurcation, for instance. Yeah. Yeah.
So I'm thinking more applied, and now I'm working with Jos Bos and Rick from the computational lab, and we're using the biobank at the PhD data, the anxiety symptoms, together with NMR, and then we extrapolate on cardiovascular diseases. And I'm thinking now how they apply this methodology, and what we're trying to build a network, tribe of that network. I'm thinking what this methodology will give us, like, do you think that it will help us maybe identify central nodes or weak connections?
Well, it depends a little on the data that you have and the question, because okay, so the biobank is huge database, so it has all kinds of behavioral data, but also physiological, brain, yeah. And that matters a lot for what you can find also if you try to put them together, because if you try to put together physiological or biological data with behavioral data, usually you end up with networks that have no connection whatsoever between these two different sources. We don't always know the reason, but the characteristics of the type of data are very different. And so it leads to them not being highly correlated or associated. But so, and in general, from what can you learn from this methodology? Well, if you are interested in the types of variables that influence other variables, then I would say you need some kind of causal information. If you just have observational data, then one way of doing it is turning to particular algorithms like the ones from Pearl or Spiritus, Gleamer and Shines, or many other persons, causal discovery. That will give you some evidence, but in most cases it will just tell you, I don't know. But for some cases it will say there's no evidence for confounds, and then you could say, well, there's some confidence that there might be some causal influence here. And I think that would be a reasonable starting approach. Yeah.
These graphs that you shown here, they are sort of inferred using the Ising model.
Yes, yes.
Have you already tried looking at inferring graph structures for this generalized Ising model?
No.
You expect it to be very similar?
Well, not at all. We did. But we looked at the one where we only have 3 categories, so 0 in between. And we looked at it not with the Ising model like this, but with the Bloom-Capell, which has an additional term to punish for the fact that or cost term that says, well, if you're either 1 or -1, then that is also a negative contribution to the Hamiltonian. And in that case, we applied it to data from the stemwijzer. So people giving their opinions about things to do with voting. Are you in favor of euthanasia, etc., etc. And there, it's not. It doesn't come up with the identical situation or identical network, but very close. So we tried the Ising model and the Bloom-Capell model. But for the Bloom-Capell model, the interest is mostly that also people fill in zeros. They say, I don't know, or don't care, or I'm neutral. And we're trying to see if that correlates highly with other characteristics of people. So that's also the interest here. So what kind of different type of information or subtleties can you derive from a generalized version like this? Not only because it's more close to the data that we have, but also maybe because of the location of the magnetization or what you would expect there. But we haven't looked at the data yet for this specific one.
But can you, given that some of these questions are binary?
Well, if the questions are binary, no.
Okay.
But many of the questionnaires are not binary.
Okay. So for some of these symptoms you can ask binary or.
Some of these symptoms are binary, but many of them are not.
Yeah. Then you just throw out binary.
Like some hybrid model where you have some binary nodes and some.
Yes.
And you'd have to reassess the whole thing about what I would do to the phase transition, right?
So for estimation, we have the combined thing. So there you have binary, continuous, depending on the distribution. So Gaussian or exponential family at least. And then you can combine all this in a single network. But then to determine what magnetization will do, we did not look at it at all. I don't think that's so easy. But
Another question unrelated to what you present now, but related to your data. Is there anyone trying to cross-grain the symptoms to aggregate them in
Yes.
contrast?
Yes, many people. Yeah.
How does it work?
How does it work? Many people do many different things. So usually, in most of the cases, you are sort of forced to do it because so here you have hypersomnia and insomnia, but basically they're the reverse of each other, right? If you sleep a lot, then you certainly don't sleep a little, right? It has to be the case. So there are many variables often in these types of questionnaires that are the positive version of the negative ones or vice versa. And so you usually put them together. So that's one way of course graining. Another is that you think things are quite different, but in actuality, how people interpret particular questions seems to be very correlated or highly correlated. So they don't really measure a different thing, and then you put them together. The way they do it is very different. Some just use PCA, vector analysis. Others use walk trap algorithms or other types of things. Many different things. Yeah.
Thanks.
Thanks.